Hi all, welcome back to the class of Mechanics of Solids. Today we are going to start our second module. The first portion of second module is thermal or temperature stress. ഇപ്പോൾ നമ്മൾ ഇന്ന് സെക്കൻഡ് മൊഡ്യൂൾ സ്റ്റാർട്ട് ചെയ്യാൻ പോവുകയാണ്. അതിലെ ഫസ്റ്റ് പോർഷൻ എന്ന് പറയുന്നത് ടെമ്പറേച്ചർ അഥവാ തെർമൽ സ്ട്രെസ്സസ് ആണ്. എന്താണ് ഈ ടെമ്പറേച്ചർ സ്ട്രെസ് എന്ന് പറഞ്ഞു കഴിഞ്ഞാൽ ദ സ്ട്രെസ്സസ് ദാറ്റ് ആർ ഇൻഡ്യൂസ്ഡ് ഇൻ എ ബോഡി ഡ്യൂ ടു ടെമ്പറേച്ചർ ചേഞ്ച് മൂലം ഒരു ബോഡിയിലേക്ക് ഇൻഡ്യൂസ് ചെയ്യുന്ന സ്ട്രെസ്സുകളെയാണ് നമ്മൾ എന്ത് പറയുന്നത്, തെർമൽ ഓർ ടെമ്പറേച്ചർ സ്ട്രെസ്സസ് എന്ന് പറയുന്നത്. When there is a change in temperature of a body, it undergoes expansion or contraction. ഒരു ബോഡി ഹീറ്റ് ചെയ്യുമ്പോൾ അല്ലെങ്കിൽ അതിനകത്ത് ടെമ്പറേച്ചർ ചേഞ്ച് സംഭവിക്കുമ്പോൾ എന്ത് സംഭവിക്കും? ബോഡി മേ എയ്തർ എക്സ്പാൻഡ് ഓർ കൺട്രാക്ട്. ഒന്നുകിൽ ബോഡി എക്സ്പാൻഡ് ചെയ്യും അല്ലെങ്കിൽ കൺട്രാക്ട് ചെയ്യും. ഇഫ് ദ ബോഡി ഈസ് നോട്ട് അലൗഡ് ടു എക്സ്പാൻഡ്, ആ ബോഡിയെ നമ്മൾ എക്സ്പാൻഡ് ചെയ്യാൻ അനുവദിക്കുന്നില്ല, ഫ്രീലി എക്സ്പാൻഡ് ചെയ്യാനോ കൺട്രാക്ട് ചെയ്യാനോ അനുവദിക്കുന്നില്ല എങ്കിൽ ദ സ്ട്രെസ്സസ് ആർ സെറ്റപ്പ് ഇൻ ദ ബോഡിക്കുള്ളിലേക്ക് സ്ട്രെസ്സ് സെറ്റപ്പ് ആവും. അങ്ങനെ ഇൻഡ്യൂസ് ആവുന്ന സ്ട്രെസ്സസിനെയാണ് നമ്മൾ എന്ത് പറയുന്നത്, ടെമ്പറേച്ചർ സ്ട്രെസ്സസ് അഥവാ തെർമൽ സ്ട്രെസ്സസ് എന്ന് പറയുന്നത്. അതായത് ഒരു ബോഡിക്ക് ചേഞ്ച് ഇൻ ടെമ്പറേച്ചർ, നമ്മളൊരു ബോഡി ഹീറ്റ് ചെയ്യുകയാണെന്ന് വെക്കുക, ആ സമയത്ത് നമ്മൾ ബോഡി ഫ്രീ ആയിട്ട് എക്സ്പാൻഡോ കൺട്രാക്റ്റോ ചെയ്യാൻ അനുവദിക്കുന്നില്ല. ആ കേസിൽ എന്ത് സംഭവിക്കും? ബോഡിക്കുള്ളിലേക്ക് സ്ട്രെസ് ഇൻഡ്യൂസ്ഡ് ആവും. ആ സ്ട്രെസ്സിനെയാണ് നമ്മൾ ടെമ്പറേച്ചർ സ്ട്രെസ് എന്ന് പറയുക. Now consider a body is heated to a certain temperature. Let this body or rod AB having its original length as L, T the rise in temperature, E the Young's modulus, and alpha the coefficient of linear expansion, and dl is the change in length or the extension due to rise in temperature. Now consider that if the rod is free to expand, then the extension of rod can be given as dl is equal to alpha into TL, where alpha is the coefficient of linear expansion, T is the temperature rise, and L is the actual length or original length of the rod AB. In this figure, AB represents the original length, BB dash represents the increase in length due to temperature rise. Now suppose that we are applying an external load P into this body. The load is acting axially. Consider its nature as compressive. And as a result of the application of this force P, the load will decrease its length. Now, due to temperature rise, the actual length of the body, due to temperature rise, the length of the body is L plus alpha TL. And after the application of the force, as a result of this applied force, the length is reduced to L. From L plus alpha TL, the length is reduced to L. Now, the compressive strain produced in the body can be equated as decrease in length divided by original length. So, the compressive strain can be equated as decrease in length divided by original length. That is equal to decrease in length is alpha TL divided by its original length L plus alpha TL, which is equal to alpha TL by L. That is equal to alpha T. L and L gets cancelled, and which is equal to alpha T. So we obtain the compressive strain as epsilon as alpha T. Since the load is compressive in nature, we will get the compressive strain which is equal to alpha T. But we know that the modulus of elasticity E is the ratio of stress and strain. So we can write the stress as the product of strain and modulus of elasticity. That is, stress is equal to strain into modulus of elasticity. And we can also calculate the load or thrust on the rod as the product of stress and area. We have already calculated the strain as change in length by original length. The change in length, it is represented as dl, which is obtained as alpha TL, and the original length is L plus alpha TL. So we obtain the strain as alpha T, and now the stress is equal to strain into Young's modulus, that is alpha T into E, and the load will get us the stress into area, that is alpha TE into A. Now the calculation of thermal strain and temperature stresses. There are two cases for calculating the thermal strain and temperature stresses. The first case is in such a way that the expansion is prevented. That is, as a result of the expansion is prevented, a stress induces. That stress is known as temperature stress. So, obviously, there occurs a strain which will be equal to change in length by original length, that is equal to change in length, which is calculated as alpha TL divided by L, that is equal to alpha T, which we have already calculated. And now the stress induced, since the expansion is restricted, the stress is known as thermal stress, and which will be equal to the thermal strain into modulus of elasticity. We obtained the thermal strain as alpha T into modulus of elasticity alpha TE. Therefore, thermal stress is equal to alpha TE. This is the case where the expansion is prevented. Now the second case. The case 2 is when the support yields by an amount equal to delta. If the support is yielding by an amount which is equal to delta, then the actual expansion will be equal to the expansion due to rise in temperature minus delta. When the support is yield by an amount delta, the actual expansion will be equal to expansion due to rise in temperature minus delta. We know that the expansion due to rise in temperature is alpha TL. So actual expansion will be equal to alpha TL minus delta, since alpha TL is the expansion due to rise in temperature. Now we have to calculate the actual strain. Actual strain is the ratio of actual expansion to that of original length. We have found out the actual expansion as alpha TL minus delta. The original length is L. Therefore, the actual strain is obtained as alpha TL minus delta divided by L, where alpha TL is the expansion due to rise in temperature and delta is the amount of yielding. Therefore, the actual strain is the ratio of actual expansion to original length, and it is equal to alpha TL minus delta divided by L, where alpha TL is the expansion due to rise in temperature, delta is the amount yielded by the support, and L is the original length. So now we are going to calculate the actual stress. The actual stress is the product of actual strain and Young's modulus. We have obtained the actual strain as alpha TL minus delta divided by L into the modulus of elasticity will gives the actual stress. So in case 2 we have calculated the actual strain and actual stress. The actual strain is obtained as alpha TL minus delta divided by L, and the actual stress is obtained as alpha TL minus delta divided by L into E, where E is the Young's modulus. So now we have calculated the thermal stress and strain and the actual stress and strain for both the cases. The case 1 is the expansion prevented by supports. In such cases, the stresses developed will be known as thermal stresses and the strain produced will be known as thermal strain, which is calculated as thermal strain is equal to alpha T, where alpha is the coefficient of linear expansion and T is the rise in temperature. The thermal stress is obtained as alpha TE, where alpha is the coefficient of linear expansion, T is the rise in temperature, and E is the Young's modulus. And in case 2, when the support yields by an amount or by a distance delta, we have obtained the actual strain as alpha TL minus delta divided by L, where alpha is the coefficient of linear expansion, T rise in temperature, L the actual length, delta the amount of yielding, and L is the actual length, and the actual stress is obtained as actual strain multiplied by Young's modulus, which is alpha TL minus delta divided by L into E. So that's all. Hoping that you have understood about the thermal or temperature stresses. Okay, thank you.